things that have taken place in the past.
Notice this screwdriver.
High voltages do strange things at times.
Those are insulators, long insulators, the fiberglass insulators are metal.
Audio processor. And switching. Computer controls for the antenna switching. These are T4 transmitters, the Quechua
Those are
transmitters.
10 kW. Does this clock work? It should. I got a red light on it. I don't know what happened.
It's running at reduced power at the moment.
I can always stop it. Oh, stop it more speed.
Right, it's TV back. It's probably not able to do it.
Here it's called.
And here we see the transmitter with the doors open. The tubes located inside that wall there.
Really doesn't work.
Okay. If I want to stop it, here it is. Just to stop it.
It'll be right there.
Spring.
Now that which went out, was it some people talking right then, or was it recorded?
Okay, I'm going to stop it here.
All right, go to the same screen and read it digitally.
They had a link, microwave link from their studios, which was 11 miles away, where they had 6 lines. They called them lines, but they were microwaves. And they had a control room there where all everything was taped and put on the air. They made this in 8 hours before. And they could handle up to 6 lines of programming at a time. Coming into these audio processors, they're processed and sent out to the different transmitters. Now let's see how they're doing that.
Here we have a digital readout. There's some reflection from the glass, but we have a digital readout of the same parameters.
That's the engineer who designed this transmitter.
Gives credit to engineer Herb Jacobson who designed this transmitter and controlled the
Now here's where the power is coming in from the
electric
power plant.
the city of Quito when we're selling.
We were selling some power because we were producing more than what we were
He
using.
remotely controls our generators in the generator house.
Voltage is coming in. There's our substation from the hydro plant.
So it is all controlled, or mostly controlled, from right inside the building. So you go on here to the right, back here is the swimming North American array of antennas.
Okay, now let's
The American,
see this.
North and South.
I've reached those ribbons hanging out there holding a reflector.
South is North American. Okay, we're looking here at the top of the antenna, right in the center of the picture. There is one dipole array on each side.
That's kind of a takeoff from the here. See this?
Quite
It's right, it's really a unique matching engineering feat to match all.
one thing that's interesting here is the array of feed lines coming out of the side of the building.
We have 32 antenna systems. You hear that audio? The mechanical
These
speaker.
lines run out here to antennas.
Danger.
Stay away from the antennas. High voltage. Danger.
There's a lot of RF in there.
This antenna is
Okay, go to the
14 meters and beaming to Europe. This antenna was actually conceived at Elkhart in Clarence Moore's office. Some of the elements, some of the elements, I guess we say, were tested there. And then we shipped out, keep that out installed here. Forget it here.
The problem was, like I say, a mismatch. Now what I had to do was get on that antenna, say disconnect the feed line, and take an impedance reading of the antenna. Then I had to put in a stub and a transformer. Now if you look over here on the other feed line over here, there's a little stub hanging down on this feed line. I don't remember if it was an open or shorted stub. But what you do is when you have a mismatch, you have two components. You have a reactance, and you have an impedance, a resistance mismatch. The reactance is either positive or negative, capacitive or inductive. You take that out with a stub. Then you use a transformer to match the impedance, the resistance. For instance, if you have a 100 ohm line here and a 50 ohm line here, you want to match them? Well, if you put them together directly, you have a mismatch. You have that ham radio. But if you put in a quarter wave transformer at that frequency, at 75 ohm transformer, that would match from 50 to 100 ohm. I mean, it's basically that frequency. And we had written a number of computer programs, just little short basic programs. We could calculate, okay, wire, this diameter, this spacing is this much impedance. Certain number of wire, certain spacing is this X impedance. And we could calculate what it took. And I found those utility programs tremendously useful. And you just go to the computer and hook in your introduction. And so what I did was put in a transformer and a matching stub. There's no more talking out in the air like that. So I'm running a little car. And he says, no problem. And so they put it up to 125,000 watts instead of 500. And it operated. And okay. They operated that night, and the next morning they tried to bring it up. And it wouldn't operate. I went out next morning and Sunday morning, but it wouldn't come up. And I knew that transmitter was scheduled for a Czechoslovakia broadcast. And that was the time when communism was. And I knew my knees was like, Lord, unless you help me resolve this, that program got to be on the air. And then I went back out and worked and found out down in the electronics of this great big 100,000 watt transmitter was a little RF driver that was starting the very first stages of the LF. And I was measuring and checking voltage and so on. And I found a cathode resistor in the tube circuit of that driver that had changed value.